Hello, in this video, we're going to cover surface integrals. Surface integrals as a topic are very similar to line integrals. It's just you're extending basically by a dimension, right? So instead of going through and calculating, the line integral is when you go through and you calculate the sum of a function over a line. A surface integral is going to be calculating the sum of a function over a surface. Okay, so let's go ahead and just jump right in. Suppose every point in R3 is given a value by f of x, y, z. Suppose we have a surface S, and that surface could be defined either parametrically or in a traditional function format. Okay, so in terms of the picture I'm going to draw a sketch. That sketch will be using a parametric surface form, but you can go through and have surface integrals defined using our traditional function format. I will mention one kind of exception or extension to this idea, when we get to it. All right, so the idea is we've got some surface. It's kind of folded over, so it's represented parametrically in terms of u and v. Okay, so what we want to do here is we want to go through and add up. All right, so this is our problem. Let's actually write our problem on here. So here's our problem that we want to solve. We want to go through and find the value of f on the surface S. Okay, so again, this is the same thing that we did with line integrals. We went and just calculated along a curve the function value at each point, and we just added all those up. So the same thing here. We want to go through and we want to just go to every single point on this surface. We want to calculate the function value, and we just want to add all those up. So how do we do that? Well, we use the same technique that we did with line integrals, and that is we go through and we break up the object into pieces. We calculate this function times surface for each one of the little pieces, and then we add all those up. And when you do a summation like that, you'll end up getting an integral. All right, so first let's go through and kind of cut this up into pieces. So this is what I just kind of did. I went through and said, all right, well, let's just say we went through and cut it like this. So this is saying this is the direction that u goes as we change u along the surface, and then we'll say that this is the direction that v goes. V goes this way as we trace along the surface. And so when we do this, we'll end up getting a bunch of little patches. And what we want to do is we want to go through and find the amount of function value on each patch. All right, in order to do that, what we're going to do is we're just going to grab one patch. We'll say we're going to grab this patch here. Say that's a representative patch. And then if we can go through and find the amount of f times surface for that patch, we can then go through and add up a bunch of those, to represent all the other patches, and end up with an integral. So let's go ahead and do that. All right, so let's do that on the next page. So we're going to start off with that patch. All right, and we'll say it looks like this. Okay. We're going to go through and we're going to just grab a point somewhere on the patch. Now, it doesn't specifically matter where that is, because again, what we're going to end up doing is we're going to end up taking, once we go through and come up with a formula, we're going to end up taking the number of patches and have them go to infinity, and they're going to come infinitesimally small. And the location of the point is not going to matter once you have these infinitesimally small patches. But to start, we're going to go through and we're just say let's just pick a spot. And we'll say that spot on our patch is going to be point. It's going to be a point Pij. So it's the ijth. So this is the ijth patch. So that's what the ij stands for. This is the ijth patch. And we're just saying we're just grabbing a point somewhere on that patch. Also, we're going to let. We're also going to say let. All right. So suppose. Suppose Pij is on the patch. And we're going to say let the area of the patch be change in Sij. Okay. So the reason I'm using an ij for the area is that the area of the patches are not all going to be the same. Okay, so you don't have to have the exact same area for every single patch. Again, as we take the limit as the number of patches goes to infinity, then those areas will become infinitesimally small, and it won't end up mattering. That the fact that they're not exactly the same for each one. Okay, so once we've got a point on the patch and we've got the area of the patch, we can go through and we can find f of Pij times change in Sij. This is going to be the function value, again, somewhere on the patch. Doesn't matter where that is, because again, when we take the limit as the number of and go to infinity, it's going to become really small. And it's not going to matter exactly where you calculate that. And then we also have the area. So we've got f times area. And so this is going to give us the amount of function value for this piece. Okay, the idea being here, if you go through and you have the function value, if you went through and had the function value and just kind of distributed it all over the entire piece, if you added all those up, that would be the same thing as taking the function value, assuming they're all the same, that would be the same thing as taking the function value at one spot and multiplying by the area of the patch. Okay, and so this goes through and does accomplish our objective, which is to find the amount of f on that area, on that patch. Okay, and so from there, the only thing that we need to do is just to go through and say, all right, well, what we want to do, so this is, hold on. This is the area, this is the amount of f for this patch, for the ijth patch. Okay, so the only thing we need to do after that to go through and end up adding up all of the f value, the amount of f, is to take this and just sum it up, right? So if we go through and do summation, f of Pij times change in Sij, we do a summation, another summation, we vary I from 1 to n, we vary j from 1 to m. What this is going to do is it's going to take, instead of just having this patch, it's going to end up adding up all these strips of patches. So we're varying I and j until we go through and add up all the patches, and then we're taking the limit as the number of patches goes to infinity. Okay, if you do that, then what happens, this double summation turns into an integral, and we have f. And so instead of putting Pij here, I'm just going to put a generic point, right? Because Pij was a point. And then instead of putting change in, as we're accustomed to, whenever we do these limit summations, the change in symbol goes away. Then ij is, again, is also going to go away. And so we're just going to put ds to represent surface area. So here we have, here's our f value, and here's our surface area for a patch. And if you go through and add all this up, then this is going to end up, this is across the patch, this is going to end up getting us, instead of the amount of F for a single patch, this is going to give us the amount of F for the entire surface. Okay, and so the similarity with line integrals here is that this is a conceptual write-up. This is not the actual definition that you use. Oh, and one other thing too, before I forget, I was going to write it down here, but I didn't leave myself enough space. This is frequently shorthanded, just like line integrals are, into f dot d capital S. Okay, and so if you see this, they mean this, right? They mean to go through and calculate a surface integral. So yeah, this is the shorthand format. And again, I'm going to write over here. So this is the conceptual. So similar to line integrals, if you go back and watch the line integrals video, there is a conceptual definition for line integrals, and then there's an evaluation definition. So this is the conceptual version, the conceptual definition for a surface integral. So what is a surface integral? It's function times surface area. That's what the ds stands for here, surface area. Okay, so just like if you go back and watch the line integrals, it's function times arc length, right, in that video. Okay, anyway, moving on. So how do we get from here to the evaluation version? All right, well, so to do that, we're going to go through and we're going to use our function definitions. So first, let's go through and suppose our surface is defined parametrically. So suppose we have R of U and V defines the surface. Okay, then what we're going to do, we're going to take that F of X, Y, Z ds, and I'm just going to go through and I'm going to replace stuff. Okay, so instead of x, y, z, well, what do we know about r of uv? We know r of uv equals x of uvi, if we just write it out, plus y of uvj plus z of uvk. So if you write out the definition for our parametric surface, we've got a definition for x, a definition for y, and a definition for z. And what we're going to do is we're just going to pop those in for x, y, and z. Okay, so we're going to have f of x of uv, comma y of uv, comma z of uv. Okay, and that takes care of translating over from this conceptual form, which doesn't even really make sense if you look at it closely, because you look at this, you're like, wait, so I've got x, y, and z. That's 3 variables, but I only have a double integral. Double integral is only over 2 variables. That doesn't even make any sense. And so, again, we're shifting over from this conceptual version, something that we don't really take seriously. It's just a shorthand way of representing the surface integral, over to something that we can evaluate, and you'll notice that we're using u and v, u and v, u and v, so we actually are changing over to something that only has 2 variables so that we can do our double integral. Okay, and then ds, so ds, where did that come from? If we just go back to our definition, ds, change it, oh, that was the surface area for the patch. So what we just want to do is we want to go through and replace that with our surface area definition. So our surface area definition, for a parametric surface from the last video is r of u cross r of v dA. And then once we've done that, we can change our double integral here. This is going to be in terms of u and v, and we're just going to change the letter from s meaning across the surface to, we'll use D here to represent the domain for U and V. Okay, and so this definition here, this definition is one that we could go through and actually evaluate. We could go through and we could, assuming that we have the surface defined parametrically, we could substitute here, substitute here, substitute here, create an F that's all in terms of U and V. We could find the partial with respect to U, partial with respect to V, cross product it, length it, and then we would have something that's all in terms of U and V, and we would end up with a double integral that has all UV stuff, and we could actually integrate over the domain for U and V. So this format is the evaluation version, and so anytime we're actually asked to go through and calculate a surface integral, this is what we will be calculating, not this. Okay, again, this is just the conceptual version, so you can recognize that what is a surface integral? It's function times surface area. That's the only thing that this is useful for, is for making sure, shorthanding that fact. All right, so this is the definition that's really important. All right, and then we could also go through and have a second case, a second evaluation case. Let's go through and suppose we have Z equals F, not F. That's a common mistake there. We're already using F, so we don't want to use, we want to use Z equals Z of XY. And that defines S. And again, we can go from our shorthand form here, S of F of X, Y, Z, ds. Now we're going to translate this over. We're keeping F here. And what we want to do is, we've got too many variables. How do we get rid of some variables here? Well, we use our surface definitions. You're going to have X, Y, Z of X, Y. You notice if you do that, then this whole thing here, this whole F, is going to end up all in terms of X and Y. And then we're going to dot product it with our surface area. So it's been a bit since we covered surface area. It was in the previous chapter, but the definition for that is the square root of Z differentiated with respect to X squared plus Z differentiated, the surface differentiated with respect to Y squared, plus 1 dA. And again, now that this is going to, if you go through and take the derivative of Z with respect to X, you're going to get X and Y stuff. The derivative of Z with respect to Y is going to be X and Y stuff. So we got nothing but X and Y stuff here, nothing but X and Y stuff here. And so we're going to have all X, Y's for our integral, which we can then go through and evaluate over the domain of X, Y. Okay, so I mentioned earlier that there are variations for our surface, and that I will talk about them when we get to that point. So this is what I meant as this point right now. So I'm going through and I'm assuming that my surface is defined in terms of Z, where Z is by itself, and we have X's and Y's on the other side. So just to give you an example, it would be like if we had Z equals X squared Y, this would meet that requirement. What if we had X by itself, right? Instead, if we went through and we had X equals Z squared Y, and this was my surface, can I go through and use this definition? Absolutely not. However, you can, with a very slight variation, go through and use it. And that's just to kind of, replace things, substitute things. And what we're going to do is we're just going to go through, and anywhere there's a, well, I'll just write it out. No, easier to just to write it out than try to explain it. We're just going to go through and switch things around. All right, so if X is the function, X is the variable that's by itself, then where the X is where we're going to end up putting our function. So we're going to have X of Y comma Z, and then Y and Z will stay as they are. And then here, instead of, this format, we'll have 1 plus X differentiated with respect to Y squared, X differentiated with respect to Z squared. So you're just moving it, you're just moving everything around, just rotating things. I mean, maybe rotate's not the right word, but you get the idea. You're just swapping things around so that it all kind of makes sense, right? So if Z is by itself, then we substituted for Z. If X is by itself, then you substitute for X. Okay, and so this second format would be the case if we were going through and we had x equals x of y comma z. And so you can go through and you could figure out, what the third version would be if we had y as a function of x and z instead. So there's going to be 3 different cases here. Now, there are not 3 cases for the parametric version, just the one. Okay, so with those definitions in mind, let's actually go through and do some examples. The instructions here are to calculate the surface integral. All right, and so we've got, here's our first problem, and they say go through and calculate x, y, z ds, and they tell you that s is the cone defined by x equals u cosine v, y equals u sine v, and z equals u. And they also tell us that u varies from 0 to 1, v varies from 0 to pi over 2, and that's it. That's the information they give us. Okay, so to go through and use so if we go back and take a look, these are the definitions we've got. So what did they give us? Did they give us z as a function of x, y? No, they went through and they gave us a parametric definition. So the parametric definition, that's our vector function form. So, this we went through and, we wrote it out in terms of r in a couple spots. So I'd say the first thing to do maybe is to go through and rewrite this. This is r of uv equals u cosine vi plus u sine vj plus uk. So I would go ahead and just rewrite this into the r format so that we can, use because we do end up using that r format in our problem. Okay, once you've done that, the next thing we're going to do is to go through and just, actually, hold on. The next thing we should do, I was about to skip ahead. The next thing we should do, actually, let's go ahead and calculate this quantity first before we go through and just do the substitutions for x, y, and z. Just as a quantity, it's something to be done off to the side. So if we do r of u, you're going to end up getting, so if you differentiate u cosine v with respect to u, you're going to get cosine vi plus sine vj plus k, right? So that's our derivative with respect to u. Derivative with respect to v, you get negative u sine vi plus u cosine vj, and that's it. And then ru cross rv, ijk cos v sine v 1, negative u sine v, u cos v 0. So we're going to get I times 0 minus u cos v minus j times u sine v, and then plus k, and it's going to be u cos squared plus u sine squared. Since cos squared plus sine squared is 1, if we have u cos squared plus u sine squared, we can go through and just put u for that, right? And that's because sine squared plus cosine squared is 1. So u cos squared plus u sine squared, you could factor out the u and you'd get u times sine squared plus cos squared, which is going to be 1. And so you're just going to get u. All right. So we kind of ran out of space here, but we can figure out the length of ru cross rv in a minute. Okay, so now this is what I was about to do earlier. We're just going to go through and substitute. So what is x? X is u cosine v. What is y? U sine v. What is z? U And then we want to go through and multiply that by what? The length of RU cross RV. Let's do this. Let's do length of RU cross RV. dA, d. And now we can go through and figure out what that is. Actually, let's simplify this while we're at it. U times U times U, that's going to be U to the third. Sine V, cosine V. And then what would this actually end up being? We're going to get square root, right? The length of this vector is going to be the square root of the sum of the components squared. So we're going to get U squared cosine squared V plus U squared sine squared V plus U squared dA d. What is this going to turn into? Again, sine squared plus cosine squared is 1. So you could factor out the U squared and you would get U squared times sine squared plus cosine squared, which again is 1. And so you're just going to get U squared there. So you get U squared here plus another U squared. That's going to be 2U squared. The square root of 2U squared is going to be square root of 2U. And then you could put the other U in here with U to the third. So we're going to have U to the fourth. Sine V, cosine V, dA. All right. To go through and evaluate that, we could evaluate this. We could do it on the next page. We're going to get square root of 2, double integral, U to the 4, sine V, cosine V, dA over dr. It's just copying that over. All right, and so what should my order of integration be here? It doesn't matter, right? If you go through and you look, we've got U from 0 to 1, V from 0 to pi over 2. When you have constants for your bounds of integration, the order of integration doesn't matter. So let's just do, let's do U first. Get root 2. The antiderivative of U to the fourth can be U to the fifth over 5. 0 to 1. Sine V, cosine V, dV. Plug in 1, we get 1/5. So we're going to get root 2 over 5. 0 to pi over 2. Sine V, cosine V, dV. This is a U substitution. We get U equals sine V, du equals cosine V, dV. dV. So we're going to get root 2 over 5. Plug in 0 into sine, you get 0. Plug in pi over 2 into sine, you get 1. And then this is U du. So we've got root 2 over 5, U squared over 2, 0 to 1. Plug in 1, you get a half. So we're going to get root 2 over 10. All right, and that is our value for our surface integral. All right. So again, to go through and interpret, so if we want to interpret that result, what is that? It's the sum of the x coordinate times the y coordinate times the z coordinate across the cone that's defined by our surface. So if you go to every point on the cone, take x coordinate times y coordinate times z coordinate and add all them up, you get root 2 over 10. It's kind of cool, actually. It's kind of neat. All right, let's try another one here. We have the surface integral of xz ds, where s is the part of the plane (2x plus 2y plus z equals 4 in the first octant. So this time they gave us the surface in terms of x, y, and z. And so it would be easiest to go through and use that format, use the second format, let's use the second formula, where we go through and we get z by itself. So we can just solve for z. We get z equals negative 2x minus 2y plus 4. Okay, and once we've done that, the next step is to go through and find the surface part of the definition, right? So we want to go through and find this. We'll do this part last. So let's go through and do this next, just like we did for the previous problem. So we need z differentiate with respect to x, which is negative 2. We need z differentiate with respect to y, which is also negative 2. And then if we just take those and just pop them into our formula, so our formula is z differentiated with respect to x squared plus z differentiated with respect to y squared plus 1, just pop them into that formula. We're going to get negative 2 squared plus negative 2 squared plus 1, right? And so what is that? That's going to be 4 plus 4 plus 1, that's the square root of 9, which is 3. Okay, and so now we can just go ahead and make our changes here. So when you go through and you make your changes to your function, right? So in this case, this is the function. You need to go through and replace z with, you need to replace z with what the surface is defined as. So why is that? If you go back to our original equation here, right? The goal is to get everything in terms of 2 variables. So we need to have 2 variables. We can't have 3. You can't have 3 like this. And so we've got x, y, and then we go through and use the surface definition to turn z into x's and y's. And so that's what we're doing there, is using the surface definition to get down to 2 variables. So we're going to go through, we'll have x, and then we'll go through and we'll have negative 2x minus 2y plus 4 in place of the z. And then after that, we can go through and we can replace the ds. That's what we just found. That's 3 dA over d. Okay, and d here is the domain for x and y. So it's the x and y values over which our object is defined. Those are not given, and since they're not given, we need to go through and find them. How can you find them? To do that, you need to go through and sketch the object. All right, so if we're going to go through and graph this, the quickest way to go through and graph a plane, that's in the first octant like this, is to set 2 of the variables to 0, which will get you the axis that corresponds with the third. So if x and y are 0, then we're going to get the z-intercept, which is at 4. If x and z are 0, then we're going to get the y-intercept, which is at 2. And if y and z are 0, then we'll get the x-intercept, which is also at 2. So this is our object. All right, and our goal is to go through and figure out over what x, y values is this object defined. All right, so what would that be? So hearkening back to the previous chapter when we were doing double integrals and across objects, what we wanted to do is we wanted to think about what would we see if we just looked straight down the z-axis, or if we thought about just flattening this object, what would we see? We would just see this. That's the x and y values over which our object is defined. So you can go through and draw yourself another picture. All right, and what are those? So that goes from x is 2 to y is 2. I guess in that case, y is 2 to x is 2. And so we end up getting, this shape. All right, and so again, doing a double integral across this type of shape, that's something we covered in the last chapter. You want to do either type 1 or type 2, depending upon the shape. In this case, it doesn't matter. When it doesn't matter, what I typically tell students is to go top to bottom, just because it's typically easier, more accustomed to it. If you're doing top to bottom, that means you're integrating with respect to y first. Then x second. And then our y bounds will go from the bottom of the object, which is at y equals 0, to the top of the object, which is this line. What is the equation for this line? Well, it's a line that has a y-intercept of 2 and a -1 slope. So it's going to be y equals -x plus 2. So you could pop that in there. And then what x values do we go over? Well, from 0 to 2. Okay. Oh, and I forgot our 3. Let's just put the 3 up front here. All right. And then so to go through and actually evaluate that, we could multiply this out. So we're going to have -2x squared minus 2xy plus 4x dy dx. Okay, switch this over to the next page. 3, 0 to 2, 0 to -x plus 2. What do we have? That's going to be, oops, that's going to be -2x squared -2xy plus 4x dy dx. And we'll just go through this really fast. So the antiderivative of this with respect to y is going to be -2x squared y minus xy squared plus 4xy, 0 to -x plus 2. And then we'll get -2x squared times -x plus 2 minus x, -x plus 2 squared plus 4x, -x plus 2, 0 to 2. And then we can multiply all that out. This is going to be 2x cubed minus 4x squared. Let's see, what's this going to be? So we're going to have x squared times -x. It's going to be -x cubed. Then we're going to have minus 4x times a -x, so plus 4x squared. We'll have positive 4 times -x, that's -4x. And here this is minus 4x squared plus 8x dx 3 integral. All right, what do we got here? So x cubed, 2x cubed minus x cubed, we're going to have x cubed. -4x squared, positive 4x squared, -4x squared. 8x and -4x, we get 4x. Antiderivatives here, so we got x to the 4th over 4 minus 4/3 x cubed plus 2x squared, 0 to 2. Plug in 2, we got 16 over 4, that's going to be 4. 8 times -4, that's -32 thirds plus 8. That's 3. 12 minus 32 thirds. That's 36 thirds minus 32 thirds. That's 4 thirds. And we get 4. All right. Assuming I didn't make any mistakes. Hopefully there's no mistakes in there. Okay. I did go through and come up with a third example, mainly because I wanted to go through and show an example other than this case and this case. So one of these kind of alternate cases. And I wanted to make sure that that was clear here. Let's go through. I accidentally added an extra page. Let's use this extra page. So what we've got is surface S, y squared z squared ds, and S is the part cone. Y equals the square root of x squared plus z squared, 0 less than or equal to y less than or equal to 3. Okay, so similar to the last example, we've got a surface that is defined in terms of a single variable, or in this case, one that could be defined in terms of a single variable. And so what we want to do is we want to go through and use, these formulas here at the bottom. The difference is that the previous example, we had z by itself. This time we have y by itself. So we want to use a variation on this where we've moved things around, for when that's the case, for when we have y by itself. All right. And so the formula that you're going to get there, let me just go through and write it on this page before we do this. So we're going to have f dot ds. And then how are things going to get moved around? Well, normally you have f of x, y, z. In this case, we're going to have x, and then we're going to have y of x, z, and then we'll have z. All right, since y is the variable that's by itself, that's the one that you end up kind of replacing with using the surface definition. And then the variation here for the surface part is going to be, instead of having z differentiated with respect to x, we're going to have y differentiated with respect to x squared. And then instead of having a z differentiated with respect to y here, we'll put 1 there for that guy. And then here we're going to have y differentiated with respect to z squared. Okay, so this is the definition that we're going to end up with when we move everything around, to represent the case where we have y by itself instead of z by itself. All right, and so just like the last two, let's do the surface part first. So we want to go through and differentiate y with respect to x. If you do that, you're going to get 1/2 x squared plus z squared to the negative 1/2 times 2x. The 1/2 and the 2 cancel, and we get x over the square root of x squared plus z squared. Then take y and differentiate with respect to z. And that guy simplifies to that. And then if we go through, take those, pop them into our formula and square them, what's going to happen here? Let's give ourselves plenty of space. So we're going to have y differentiate with respect to x squared plus 1 plus y differentiate with respect to z squared. That's going to equal, all right, this squared is going to be x squared over x squared plus z squared plus 1. This squared is going to be z squared over x squared plus z squared. And if we add those, what happens? This plus this, we're going to get x squared plus z squared over x squared plus z squared. So that's going to become 1. So this whole thing ended up simplifying into root 2. So this piece here simplified into root 2. All right, so that part is done. To go through and do the rest of the problem, what we need to do is we need to figure out what this is going to change into. Let's do that. 2 pages down the line. All right. So we're going to have if S y squared, z squared, and the ds part is the part we just did. That's root 2. So let's do this. Actually, you know what? Let's do sorry. Let's do this. So we have ds s, this equals over d, and this part we just figured out is root 2. So how do we go through and simplify this part? So what you want to do, we go back to our definition here, is you want to take wherever there's a y, you want to replace it with your surface part. Wherever there's an x and wherever there's a z, you just want to leave it. And we'll end up with just x's and z's here if you do that. So leave x's alone, leave z's alone, replace y's with what the surface definition is. All right, so we're supposed to leave z's and x's alone, but replace y with the surface definition for y. And the surface definition was square root x squared plus, so y equals the square root of x squared plus z squared. That's this. Then leave z squared alone. Then ds we just figured out is root 2. Whew, all right. So what is this? This is x squared plus z squared times z squared dA. And we can move the root 2 inside here. And so what we need to do next is we need to go through and figure out what are our bounds of integration and our order of integration. To do that, we need to know what, what the x and z values, we need to know what we're integrating across. Like what is our surface? What does our surface look like here? And so if you look at it, if you go back to it, it's S is the part of the cone. So we've got a cone, the part of the cone where the y values go from 0 to 3. All right, so actually, let's go ahead and just sketch this, the next page. All right, so we've got y equals the square root of x squared plus z squared, y going from 0 to 3. What does that look like? All right, so we know it's a cone. If you go through and you set x, if you go through and set z to 0, you'll get y equals plus or minus x. So that's going to look, there's y equals positive x. And then over here, let's do this. There's a negative x-axis. So here's negative x. All right. And then if you set x equal to 0, you're going to get y equals plus or minus z. So here's positive z. Let's go to there. And here's negative z. Okay, and then we could go through and say, here's y is 0 right here. Let's pick a spot. Let's say this spot here is y is 3. If you go up till you hit the curve, down till you hit the curve, I guess line in this case, you go in the x direction until you hit the line, negative x direction until you hit the line, you'll end up getting the end of your cone. All right, so the question is, what are our bounds of integration? When we go through and figure out our bounds of integration, what we want to do is we want to imagine the shadow of an object, or flattening the object, or the widest point of the object, however you want to think about it. In this case, when you have a function of y like this, or a surface that's defined in terms of y, you're looking at it from the perspective of the y-axis. So normally we look at it from the perspective of the z-axis. That's because z is by itself. When y is by itself, we're looking up the y-axis. And what would we see? We would just see this outer circle here. That's the only thing that we would see if we did that. And so that is going to be our bounds of integration, is this circle. All right, so what is that circle going to be in terms of x and z? Well, if you just took it and imagined flattening it onto the XZ plane. I don't know if you really need to do this, but it's going to look like this, right? Something like that. What are our bounds going to be for that? What is this point here? What is this point here? What is this? This looks like a circle. How do we figure any of that out? Okay. Well, the way that you can go through and figure that information out, how big this circle is to go back to the stuff that you were given that defined it. We have y is this, and we have y goes from 0 to 3. Well, if you take y equals 0 and plug it in, what happens? You get 0 equals the square root of x squared plus z squared, which if you solve this has x and z both 0. That's the origin. So that's part of the object. That's the innermost part of the object. And then the outermost part of the object will be at 3 equals 3 coming from right here equals the square root of x squared plus z squared, which gives us 9 equals x squared plus z squared. And what we have here is we have a circle of radius 3. So our z values, our x and z values are going to go over this inside of this circle of radius 3. Sorry, this is really bothering me. This bottom half is so ugly. It's a little bit better. All right. So over to our problem here, the object that we're integrating across is a circle of radius 3. What do we do with double integrals when we integrate across circles? We go through and we change them into polar coordinates. How do we change this into polar coordinates? You want to go through and use the normal translation formulas. You just want to swap out y's and put z's in their place. So normally we would have x equals r cosine theta. We would have y equals r sine theta. In this case, we're going to have z equals r sine theta. And then we'll have x squared plus z squared equals r squared. And not that we're going to use it, but tangent of z over x would be theta. Okay, and with that in mind, we can go through and we can change this over into polar coordinates. X squared plus z squared, that becomes r squared. Z is r sine theta, so we're going to get another r squared sine squared theta. dA, we use r dr d theta. Our r bounds go from 0 to 3, and our theta bounds go from 0 to 2 pi. Okay, so next we want to go through and evaluate this. So let's go to the next page. We're going to have square root of 2, double integral. We've got, what is that, r to the 5th, sine squared theta, dr d theta, 0 to 3, 0 to 2 pi. I think we got everything here. So first we'll integrate with respect to r. So we're going to have r to the 6th over 6, 0 to 3, sine squared theta d theta. And assuming my notes are correct, that's going to be, I've got 729 for that. Is that right? 3 times 3, 9 times 3, 27, 81, 243, 729. Sounds right. So we've got 729 sixths, 0 to 2 pi, sine squared theta d theta. So we should be able to simplify this. All right, so this was 243 times 3, and this is 2 times 3, so we should get a 243. And so we're going to get 243 root 2 over 2. All right, and now to go through and do our sine squared theta here, we can use the double angle identity. This is 1 minus cosine 2 theta over 2. 243 root 2 over 2. And that's going to be 1/2 theta minus sine 2 theta over 4, 0 to 2 pi. All right, so what I'm doing here, I went ahead and just took sine squared and replaced it with the double angle identity. And then I'm just integrating. So 1 over 2, that's the 1/2 theta. And then the antiderivative cosine 2 theta over 2 is sine 2 theta over 4. So technically you need to do a substitution for that, but just skipping some steps here to speed things up. We get 2 theta plugged in, 1/2 times 2 theta, so you get, or sorry, pi, 2 pi times 1/2, you're going to get pi. And then minus, this is going to be sine of 4 pi, which is 0. And when you plug in 0, you get 0 again. And so we're going to have 243 root 2 over 2 pi. Okay, so hopefully that is correct. I don't see any mistakes in here, but anyway, if you do see a mistake, you can just comment about it in the comments below. All right, so halfway there. This is a big section. So the next thing that we're going to do is we're going to go through and we're going to talk about normal vectors to a surface. Why are we doing this? Well, if you go back and you recall, I said at the beginning of this section that this section is very similar to the line integral section. And in the line integral section, half of the line integral section is on line integrals where you're adding up the value of a function over a curve. And then the other half is on work integrals where you go through and we combine vector fields with line integrals. So that's the same thing that we're going to do in this section is we're going to have the second half of this section is going to go through and combine vector fields with surface integrals. But before we get to that point, we need to go through and kind of this is somewhat a refresher. Some of it's going to be new, but we need to talk about how to define a normal vector to a surface. All right, so let's suppose that we have a surface. And we're going to start off by looking at the z of xy version because this is the version that is review. We've got our surface. Let's say we've got a point on that surface. And what we want to do is we want to go through and find the normal vector at that point. We've actually done this before as part of going through and finding the tangent plane. If you go back and watch the tangent plane section, we've actually done this before. How did we do it? Well, what we did is we went through and said, at this point, we could find the partial with respect to x. And the partial with respect to x would be the slope of the line that's in the x direction. All right, so if you were at the tangent line in the x direction, so if you go through and were to draw a curve like that, so let's say that that part of the surface has that curve, we can go through and find the slope of that curve in the x direction using the partial with respect to x. And then we can take that slope and we can take that and turn it into a vector. That's what we did in that section. And I'm going to review how to do that, but just one second here. So if you go through and draw a line, right, so that we would say that's our tangent line. The slope of that line is partial with respect to x. All right, and then you can go through, and that's the curve that's in the x direction. You can then go through and do something very similar in the y direction. So let's say the surface has a curve like that in the y direction. we can go through and find the tangent line. Say the tangent line. Oh, hold on. That was supposed to be a line. Oh, wow. I was able to erase it without erasing the black line. Well done. And then we can find the slope of that red line. The slope is partial with respect to y. And then we can take these slopes and we can turn them into vectors. So what is a slope? A slope is a change in z with respect to change in x. All right, so it's how much vertical change you get as you take a step in the x direction, a change in x size step in the x direction. So that's just our slope definition. And if we go through and set it equal to our actual slope, partial with respect to x, and anytime we've got something, we can always put it over 1, right? And it doesn't change the value. And so this is saying that we get a partial with respect to x size vertical change when we take a 1 size step in the x direction. You can then take this and rewrite it into a vector, right? So as a vector, you have a 1 size step in the x direction, no step in the y direction, and then partial with respect to x is the vertical change. And so you can define this, you can turn a slope into a vector by basically doing something like this. And then you could do the same thing for y. You get partial with respect to y over 1, and we get 0, 1, partial with respect to y. So here's your slope form for this line, and then here's the vector form, which is the direction vector for that line. And same thing for y here. And then once we have these vectors that, again, define the lines here, you can go through and you can take their cross product to get the normal vector. And all this is review. This is covered in the tangent plane video. So you could go back and watch that if you want to see more information on it. But if we go through and say, I don't know, we could say this is u and this is v, then u cross v equals 1. We need first we need I, j, k, then 1, 0, partial with respect to x, 0, 1, partial with respect to y. This is I times negative partial with respect to x minus j times partial with respect to y plus k times 1. And if you write that out, you get negative, sorry, little mistakes. We're using z here, not using f. No f's. There's a reason for that, and it's because of the fact that we're going through and we're restricting f for our surface. Or sorry, not for the surface. We're restricting f for the function value that we're adding up on the surface. All right, there we go. So you end up getting this. Anytime we have a surface, z equals z of xy, and we want to go through and find the normal vector to the surface, we could go through and do all these steps and get to here. Or we could just skip all these steps and just jump right to here. So one issue with this that we're going to cover in a moment is that there's actually a second normal vector to this surface. There's the normal vector that goes downward instead of upward. So there's also the negative of this is also going to be another normal vector to the surface. And there might be a time when we would prefer to have that one instead. Okay, so let's just do this and say, here's n. Here's n. This one points up. How do we tell this one points up? Because it's got the plus k, right? And then let's say there's also a negative n down here below. Okay, actually, before we move on to talk about our parametric surfaces, I do want to go through and spend a minute and talk about variations of this other than the negative one. Okay, and that is, what if instead of having z equals z of xy, what if we had y equals y of x comma z? What if you had a surface defined where y is by itself? What if we had x equals x of y comma z? What would we do? Well, what you can do is you can just take everything that's written here and just move it all around, just substitute it all around. Instead of drawing this picture so that it's above the xy plane, you just rotate it if you had y by itself so that it's above the xz plane. Then you'd go through and wherever there's a z, you'd replace it with a y. And then you could go through, and this would be change in y over change in x. And you'd have change and then change in y over change in z. And then you'd, instead of having z differentiate with respect to x, we'd have y differentiate with respect to x. And instead of having z differentiated with respect to y, you'd have y differentiated with, anyway, you go through, you just replace all this stuff. What happens? I'll just give you the answer in case you're like, wow, I'm really having trouble following all that. What's going to happen is instead the normal vector, you're going to end up with y, negative y differentiated with respect to x. Sorry. You're going to have negative x differentiated with respect to yi plus j minus, oh wait, no, I was right the first time. Sorry. This is actually a very difficult video to make. There's a lot of details here. And then y differentiated with respect to z. Okay. Whew. All right, so this is the definition if we have y equals y as a function of x and z. And then if you have x as a function of y and z, you're going to get, all right, so this time it's going to be I minus x differentiated with respect to y j minus x differentiated with respect to z k. All right, so, and then there's also the negatives of these. There's also, so this would be n, this would be an n that points in the positive y direction. There's also there might be a circumstance where you'd want to have negative n, which would point the opposite of this. And then there's also negative n for this one too. So we'll talk about when we might want to use the negatives of these later in the video. All right, so we've got normal vector to a surface. We went through and kind of showed where that came from. That's this if the surface is defined in terms of z. This if the surface is defined in terms of y. This if the surface is defined in terms of x. Okay, what if you have a parametric surface? What if we have r of u comma v? All right, if we have r of u comma v, let's just go through and kind of just sketch for ourselves a surface. So we've got our same surface that I've been using the whole time here, which is kind of this folded over surface. Let's say we've got some point on the surface. So again, same idea as this. We've got some point on the surface. All right, and then how could we go through and find the normal vector there? Well, so the nice thing about a parametric surface, right? So we know that, we've kind of discussed this before. If you go through and vary u but hold v constant, we can say, well, then this would be the part of the surface that would get traced out. If you go through and hold u constant and vary v, we could say that this would be the part of the surface that gets traced out. If you go through and calculate the partial of r with respect to u, you end up getting this vector, the vector that's along the curve that you would get if you held v constant. And that effectively, you inherit that from the way that we go through and handle derivatives of vector functions with one variable, right? If we had just r of t and we differentiated r of t, you get the tangent vector. Actually, I can draw a picture here to explain this. So if we've got a curve, that's r of t, right? And we know that's how that's the result if we go through and vary t for our function r. And you go through and you pick a spot on there and you calculate the derivative. What do you get from calculating the derivative of a vector function? You get the tangent vector. So that's what is the result of going through and taking the derivative of r. This is r prime of t. Well, if you just take, if you take our surface here and you only vary one of the two variables, just u, and you treat v as a constant, this curve is the same. It's not exactly the same. It's a variation, obviously, but it's the same idea as this. You're going to get this curve that's on the surface. And if you calculate the derivative of with respect to the variable that you're varying, or the other one's held constant, then you're going to get a tangent vector, just like you got a tangent vector when you only had one variable. So if v is constant and we're just varying u, then this effectively acts like this does. Okay, and so when that happens, when you go and differentiate, that means that your derivative is going to act like this derivative does, which is it's going to be a tangent vector. And then you could do the same thing of this with the v. So if this curve here represents how the surface, the part of the surface when you vary v and you hold u constant, if you differentiate the surface with respect to v, you get the tangent vector. Okay. So this guy, r differentiate with respect to u. This guy, r differentiate with respect to v. And so if we want to have the normal vector, and we've got tangent vector, which is on the surface, tangent vector on the surface, you can just take their cross product. Ru cross rv is the normal vector. Okay. Now, again, just like with the previous cases, we may also want to consider the negative normal vector depending upon the context. Okay, so we will talk about when we might want to use the negative of the normal vector instead. But there's technically, just like with the others, there's technically two normal vectors. There's the one pointing upward, and there's also the one pointing downward. All right. Okay, so I've mentioned it multiple times. When would we want to have upward pointing normal vectors versus downward pointing normal vectors? To answer that, what we're going to do is we're going to introduce the idea of a orientation to a surface. What we're going to say is that if a surface has the following shape, so it has kind of it's concave down, but it has a shape like it has a maximum, right? So it has this type of a shape. So it's got this bend in it, and the bend has a maximum value. In that case, we would say positive orientation for the surface is upward. And so in that case, if we were going through and going to represent the positive orientation, we would represent it with upward pointing normal vectors. Meanwhile, if we had the opposite of that, then positive orientation would be downward. Okay, so if we had the opposite of that, we had a shape that looked like this, right, where we have it's technically it's concave up, but we have a minimum, then we would have downward pointing normal vectors would be positive. All right, so positive orientation is downward. Let's put this instead of the. All right, and so if we're going through and we're working on a problem and we go through and use the calculation, we use this calculation for the normal vector, but our surface has a downward, like a minimum type shape, then instead of using this definition, we're going to want to use negative n. You know, and the same thing goes for this guy. And this is for n, an n that points to the right. If we had a bend in our surface so that the n pointed to the left, we'd want to use negative n instead. And so it's just a step in terms of going through and doing the problem. When we go through and do problems, we'll do it. It's a step where you go through and you just pause and you say, okay, do I want n or negative n? You know, do I want upward normal vector or downward normal vector? And again, it's going to depend upon the shape of the surface. That's kind of what we're talking about here. All right. Now, so this is all good. Upward for this, that's positive orientation. Downward for this, that's also positive orientation. However, I want to make one minor change to this in terms of interpretation, because we're going to extend this idea to closed surfaces. All right. And that is, if you thought of this as an enclosed surface, right? If I added a plate at the bottom here to make this so that it's not just a surface, but it's enclosed, right? So if I just went through and just tossed a plate here on the bottom, right? Then notice that the ends are pointing outside the enclosed object. Okay, so this is the positive orientation for this surface is upward or outward. The same thing goes here. If you go through and you put a plate here and enclose this, notice how the ends are pointing outside, is downward or outward. So that's the consistent part. If you're looking for something consistent, the normal vectors or the positive orientation is always outward. And so if we have a closed surface, like a sphere, for example, and that's actually the example I'm going to use. If we had a sphere, I'll try and draw a sphere. So this is the top half of the sphere, bottom half of the sphere, left side, right side. All right, then positive orientation of the surface is outward, meaning you're going to have upward normal vectors for the top half, downward normal vectors for the bottom half. All right, so those are that gives us our orientation and introduces the idea of orientation for surfaces. Okay. With that done, we can then go through and define what are called flux integrals. All right, so in our line integral section, the part of the line integral section that intersected with vector fields were work integrals. The part of the surface integral section that intersects with vector fields are flux integrals. Flux, I don't know if this is the technical definition, but I just think of it as means flow, like flow through. So flowing through, the idea of flowing through something. All right, so you can Google that word and see if it means what I think it means. Anyway, so suppose we have a vector field. At every point in R3. All right, so the idea here is that we've got a vector field here. And to go through and represent that vector field, I'm going to go through and put some vectors in here, but I'm not going to put a ton of them. I'm certainly not going to put one at every single point. I'll just go through and put a few in here. Let's say that our vector field just points upward, just for simplicity's sake. So we got some vectors pointing upward. This is what our vector field looks like. It's just an upward pointing vector field. And it's constant, right? So it's just K. Vector field is K in this case. But every point in our R3 here has one of these upward pointing normal vectors. Okay, so suppose we also S defines a surface. And I put it's either R of uv or it's z equals z of xy, but it could also be y equals y of xz or x equals x of yz. It could be any variation of the various rectangular coordinate definitions. Well, we got a surface in here. All right. So what I'm going to do, I'm going to go through, I'm going to try and draw a surface in here. Actually, let me erase these two bottom guys just in case. I can add those back in at the end. All right. So we got some surface in here, and I'll do my best to try and show this. All right. So we got some surface, and we're going to draw a surface that has an upward positive orientation. Okay. So it looks something like this. All right. So we have a positive orientation, upward positive orientation. Okay, and then the goal here for the problem is to go through and find the flux through the surface S, through the surface. So we want to go through and find the flux through the surface. We want to find the flow. So if the idea being, if the vector fields were modeling fluid flow, we want to figure out how much fluid flows through the surface. That's the idea. Okay. So that's the question we want to answer. How much does the vector field, the flow from the vector field, it's being modeled by the vector field, how much does that flow go through my surface S? To answer that, what we're going to do, so we've said all these black arrows, they all represent the vector field, they're all F. What we're going to do is we're going to put on here, we're going to put the normal vectors for the surface, because the normal vectors for the surface are going to have something to do with modeling the flow through the surface. And we'll talk about more of that in a minute, but I'm going to go through and I'm going to put some vectors to model the normal vectors on my picture here. So I'm just going to pick some spots, not all over, but let's say here, there's a normal vector there. Here, there's a normal vector there. Here on the backside, there's a normal vector there. Here we've got a normal vector. Right, every point on my surface we have normal vectors, right? And they all point orthogonal to the surface. Okay, so what do these normal vectors have to do with calculating the flow through the surface? Okay, well, let's just think about this for a second. If we just flattened this surface and just made it so that it was a curve, right? So if it was a curve like this, okay, and I went through and picked a spot on here and said, this is the normal vector at that spot. If we were going through and if you were asked a question, what would the fluid flow, what would the direction of the flow of a fluid have to be to maximize the amount of flow at that point? All right, so if that was if you were asked that question, so what direction would F, which is modeling the fluid flow, what direction would F have to be to maximize flow through the point where this normal vector is? Okay, well, if you're asked that question, what direction would have to be, if you think of this as a net, okay, that we've just kind of flattened so that it's just a curve. But if we think of this as a net and we had water flowing through it, what direction would the water have to be to flow to maximize the amount of flow through the net? The answer is it has to be the exact same direction as the normal vector, right? So we would want to have maximum flow. We would want F to look like this. We would want them to match in direction. Okay, that would maximize the amount of flow. Meanwhile, what would minimize the amount of flow? So this would be, so maximum would be, if we put F1 here, I was going to draw two pictures, but I don't have space. F1 would be the direction for maximum flow. If we had F2, which would be orthogonal, this would be the direction for minimum flow. So F1 would get us the maximum amount of flow through our net, and F2 would get the minimum amount of flow through the net, right? So if you put a net into a river, right, and the flow of the net is just sitting on the top, on the surface of the river, and the flow is, going orthogonal, right? Is not going, well, is parallel, I should say, not orthogonal, but it's parallel to the net, right? If this net is sitting on the surface and the flow is going this way, there's no fluid flowing through the net. You've got to take the net and actually pull it down into the water so that it is orthogonal to the flow before you'd get a lot of flow through it. So that's what the normal vectors have to do with going through and measuring flux, is that the normal vectors represent the direction that the vector field would have to be to go through and get and maximize the flow. Okay, so with that understanding, the next question becomes, what calculation could we do that would then end up representing the flow? Well, if we know that when F and N are in the same direction, we get max flow, and when F and N are in orthogonal directions, we get minimum amounts of flow, what type of calculation models that we've actually done? And the answer is, if you think about it for a few minutes, the dot product. If you calculate the dot product between two vectors that point in the same direction, you get the maximum amount of value for the dot product. And if you calculate the dot product for vectors that are orthogonal, you get 0. So what we are going to do to model the flow is we're going to say that F dot N models the amount of flow, or it gives us a measurement of the amount of flow. Okay, so with that with that in mind, taking that, what we can do is we can go through and we can take our surface and we can draw a bunch of, we can make it into patches by drawing a bunch of curves on it. We can take one of those patches, we can just grab one of those patches. We'd say that patch looks like this. We know on that patch we have a normal vector. We're saying Pij. Let's say this point is Pij. And it's somewhere on my patch. Then we can go through and we can calculate the normal vector at Pij. So the normal vector at Pij. We can also go through and calculate the vector field at Pij. And using the direction that I'm from my previous picture, we'll say that's upward. Now, obviously, it's not always upward, but we'll just say it's upward. Pij. And then we also have the area of my patch. So the area of this patch is change in Sij. All right, so if I've got a little patch and I pick a point on it, I can find the normal vector there, I can find the vector field there, and I can find the area of that patch. If I go through and take f of Pij and dot it with n of Pij, and then multiply the result. So that's going to give me a measure of how much f and n point in the same direction, which is a measure of how much flow there is there. And then I take how big the area is, then I go through and end up with a measure of flow through that patch. So this is a measurement of flux through the ijth patch, right? And this is the ijth patch. I didn't label it. And then from there, all you've got to do is just take this and sum it across the entire surface. And if you sum it up across the entire surface, you'll do that with a couple summation symbols, you know, mn to infinity, number of patches to infinity, I equals 1 to n, j equals 1 to m. This will end up adding up the f dot n, the amount of flux for every point from every patch on the surface. And this ends up turning into double integral f dot n ds across our surface. And this is our definition of flux. This is the conceptual definition for flux. This is not the definition used to evaluate flux. This is the conceptual version. Just like with the surface integral earlier in this video, we'll go through and we will do a version where that you can use for evaluating. Frequently, this is shorthanded. There's an alternate conceptual version that is shorthanded into f dot ds. So the n is combined with the ds into one component here, and you end up dotting f with ds, where ds is a vector. And so we will end up using this format more often than this format, but just wanted to start off. This is the base format, which is that f is dotted with n ds. Oh, you know what? One thing I will mention this in terms of the evaluation version, but the goal here is to figure out whether f has the same direction as n to ensure that the length of n does not end up factoring into the calculation of the flux. You want n to be a unit normal. All right, so we want these, all the n's here, we want them to be unit normals. So we will take that into account when we actually go through and do our evaluation version of, of this formula. But just wanted to mention that right here, because of that n there, that's supposed to be a unit normal, not just any old normal. Okay, let's get into the evaluation version then. Let's just jump right to it. Evaluation version for flux integrals. Okay, so how are we going to do this? Well, I kind of skipped a step here. I jumped right from I jumped right from this. I jumped right from the point format here. I didn't write out the point format. What I'm going to do is I'm going to write out the point format for these, because writing out the point format is going to be part of going through and changing over to the evaluation version. All right, so we're going to start with f dot n ds, and I'm going to write out. So this is f of x, y, z dotted with n of x, y, z, where n is a unit vector, dotted with ds. Okay. And so the next step, we're going to go through and we're going to do the same thing that we did with surface integrals earlier in this video. And it's really the exact same thing. So here we're going to basically either plug in our surface definition. Actually, not either. We are going to plug in our surface definition. All right, let's do R of UV first. So let's say this is the evaluation version for R of UV. All right, so we say we've got R of UV equals X of UV I plus Y of UV J plus Z of UV K. All right. So we're going to do F of X of U comma V, Y of U comma V, Z of U comma V, dotted with, and now n of x, y, z. What I'm going to do here, instead of going through and doing n of x of u of v, y of u of v, I'm going to replace n with what we found earlier, right? So what did we find earlier for a normal vector to a surface? Let's go back. We said this was the normal vector to a surface. So we're going to pop that in. We're going to substitute that in. Now that is calculated at x, y. That is calculated at x of uv, y of uv, z of uv. We can represent that. So we'll have r of u, and then actually, no, what? Let's not do that. We'll just put r of u cross r of v. So these are calculated at those coordinates, but it just makes it too cumbersome to put that. R of u cross r of v. However, what did I just say? I said this is a unit vector. This is not a unit vector the way that it's written. To make it into a unit vector, we would divide by the length of RU cross RV. Okay, and so that's all n. And then ds, again, this part we're inheriting from earlier. What did we say that ds was? You could go all the way back. This is kind of cool how it all builds on itself, but it's very difficult to go through and describe all of it at once in a video format like this. What did we say ds was? ds was the length of RU cross RV. So ds is going to be the length of RU cross RV dA. And now in doing this, and it's buried inside of here, but we've changed everything over to U's and V's inside of these as well. And so now we can change over from S over to D, where D is the domain of U and V that defines the surface. And if you're looking at this and you're like, oh, wait, wow, don't those cancel? Yes, they do cancel. Yes, that's exactly the idea. And so our evaluation version is going to be F of X of UV, Y of UV. So you need to change everything over into U's and V's, just like we did for surface integrals. And then you're going to dot it with RU cross RV, which are also all in terms of U and V, dA. Okay. Then you'll integrate. So this is all UVs, this is all UVs, then integrate, and the result of that will be the flux. This is the evaluation version for R of UV. Okay. And so there's one more thing I'm going to do here. I am going to actually compare this with our format, right, that we had a second ago. We said our shorthand format, this is f.ds. Right, so I said this was equal to f.ds. You can see how this and this look kind of similar. I mean, yes, we have D here versus S, F. But what I'm going to do is I'm going to go through and I'm going to take this, and I'm going to combine them and say that ds equals RU cross RV dA. And this is going to be, we're going to use this when we go through and evaluate flux integrals. So the process for evaluating flux integral is going to be to find this ds and then substitute it in and then do the integral. So it's just going to allow us to compartmentalize the problem. And so I just don't want you to be confused when we actually get to the problem, get to the point where we're doing problems. And I write, first we're going to find ds, and then I go through and I do this. I want to be clear where that's coming from. It's coming from the fact that these two, look like this. And so I'm going through and just doing this part of the problem first. Okay, and then the evaluation version. For z equals z of x comma y. And now, again, this could be for x equals x of yz, or z or x equals x of yz. It could be for any of the variations of the surface. Okay, so same thing as last time. You start off with f.n ds. Over s. That we can break that out. This is actually f of x, y, z dotted with n of x, y, z ds. Sorry, that's once you've changed over, this becomes a, oh no, that's still ds. Geez, I'm getting confusing myself. We still have a surface integral here. And now we're going to change over the variables. And so this is going to become, now it changes to d. And to go through and represent that, x stays x, y stays y, z, you use the surface. So this part is all the same as the surface integral part earlier. And we're going to use our surface integral definition that we came up with, or sorry, our not surface area. We're going to use the definition we came up with earlier. So this is the negative z differentiated with respect to xi minus z differentiated with respect to yj plus k. So that's our definition from n from earlier in this video. And now, because it's supposed to be a unit vector, we're going to go through and we're going to divide by the square root of z differentiated with respect to x squared plus z differentiated with respect to y squared plus 1. So that's all this. And we still have ds, and the definition for ds, again, from earlier in this video, is the square root z differentiated with respect to x squared, z differentiated with respect to y squared, plus 1 dA. These cancel, and we end up with f dotted with negative partial of z with respect to xi minus z differential with respect to yj plus k dA. And then the same thing that I just did a second ago, we're saying this is very similar to f dot ds, which is our conceptual version, the shorthand conceptual version for the flux integral. And what we're going to say is we're going to say that this and this, we're going to match those up, and we're going to say that ds equals negative z differentiated with respect to xi minus z differentiated with respect to yj plus k. When we actually go through and do problems, we're going to use this, and we're going to start off, we're going to find ds first. And so again, I don't want you to be confused when I'm going through and I'm doing a problem and I say, first, let's do ds, and then I write this. Okay, where that's coming from is in matching up the conceptual version with matching up the second part of the evaluation version. Okay, one other comment about this before we move on and actually start doing some examples. All right, notice that in the original problem we said that we have upward positive orientation, upward normal vectors. So when you're going through and doing RU cross RV in the problem, you do need to check to make sure that RU cross RV is oriented properly with the surface. So if you have upward pointing normal vectors, you want RU cross RV to point upward. If you have upward pointing normal vectors, then you want to have, then this is the correct definition. This definition, because it has plus K in it. If we had downward as the positive orientation because the surface was shaped differently, then instead of using this formula here with a plus k, we would want to negate this and use a negative n instead. So we'd have a positive z differentiated with respect to x, a positive z differentiated with respect to y, and then minus k. All right, so let's look at some examples. So in these examples, we're asked to go through and evaluate f dot ds across the surface. And specifically, if the surface is enclosed, it needs to be across all of the surface, all the different edges of the surface. Not enclosed. Well, I guess enclosed is probably accurate too, but is closed. All right, so for our first example, we're going to look at, they give us f, they tell us it's xyi plus yzj plus xzk. Tell us S is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the square (0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to 1. And they tell us it has upward orientation. Okay, so we're going to try and follow an organized way of doing these problems. And the first thing we're going to look to do is to find ds. ds. And so ds, when you have an upward oriented surface is going to be negative z differentiated with respect to yi minus z differentiated with respect to yj plus k. So we need to go through and find that first. Right, to do that, you need to know what the equation is for z. It's given, right? So this is z equals z of xy. And so to calculate this, we need to calculate the partial derivatives. So we can go through and do z differentiated with respect to x is negative 2x. Z differentiated with respect to y is negative 2y. And then once you've got those, you could just pop that in. So ds equals 2xi plus 2yj plus k. All right, and then once we have ds, we can go through and plug everything in. All right, so what we want to do is we want to find f dot ds. So let's just plug everything in. What is f? It's this, but keep in mind when you go and plug this in, you only want to have two variables. So you're going to go through and substitute for one of the three if there's all three there. And the thing that you're going to substitute with is your surface equation. So we're going to have xyi plus y times 4 minus x squared minus y squared j plus x times 4 minus x squared minus y squared k. So all of that is our definition for f, except reflected in two variables. Next, we want to dot that with ds, which we just found. It's written right there, 2xi plus 2yj plus k. And then dA at the end, right? And over the domain for x and y. Okay, so that's the first two steps. Step one, find ds. Then step two, write f and ds together. And when you write f, you want to go through and get it down to two variables, only two variables. If you got z's here, then you're doing it wrong. You should only have x's and y's, right? Wherever there's a z, use your surface definition to replace it. And then once you've done that, from there, you just actually calculate the dot product and then do the integration. All right, so let's go ahead and calculate the dot product, and we'll kind of go back and forth and write this over the next page. All right, so we're going to integrate here. And so what's our dot product? So we're going to have xy dotted with 2x. So we're going to get 2x squared y. All right. And then for the next one, we're going to dot this with 2y. All right, so we can do those one at a time. So we're going to have 4y times 2y. So this is going to be 8y squared. All right, 4y times 2y, 8y squared. And then next we're going to have negative x squared y times 2y. So we're going to have negative 2y squared x squared. All right, and then next we're going to have negative y cubed times 2y. So we're going to have negative 2y to the fourth. All right. And now next, we're going to have this dotted with k. And when we dot that with k, so we're just going to be multiplying it by 1. So it's really just this. So what do we got there? That's plus 4x. Minus x cubed. Minus xy squared. That's it. All right, and now we're integrating across. We've got dA over domain D. All right, let's go through and simplify. Do we have anything that simplifies? X squared y, no. Y squared, no. No, no, everything is unique. Okay, so in that case, instead of rewriting it, let's just go ahead and just change the order of integration here above. All right, so we're told that we go from 0 to 1 and 0 to 1, right? Since we have constants for both of our bounds, the order of integration doesn't matter. So we do 0 to 1, 0 to 1, and let's just do dy dx because that's typical. I think that's the kind of the standard order when you have choice. All right, so if we're going to integrate, we're integrating with respect to y. So that means we're going to get y squared over 2. The 2's will cancel, so we're going to get x squared y squared. With respect to y, this will be 8/3 y cubed. With respect to y, we're going to get minus 2/3 y cubed x squared minus 2/5 y to the 5th plus 4xy minus x cubed y minus 1/3 xy cubed, 0 to 1 dx. Plugging in 1 for all those y's, we're going to have x squared plus 8/3 minus 2/3 x squared minus 2/5 plus 4x minus x cubed minus 1/3 x. Now let's just check that. Plug in 1, x squared, 8/3, 2/3. All right, and then all of that dx. Anything simplify this time? It looks like yes. 0 to 1, we've got negative x cubed, x squared, and negative 2/3 x squared is going to be 1/3 x squared. We've got 4x minus 1/3 x, so that would be 12/3 minus 1/3. We get 11/3 x. And then 8/3 minus 2/5. I don't know, what is that? That's 40/15 minus 6/15. 34/15. Yep, that looks right. All right, and then dx. And we can integrate. So we're going to get negative x to the 4th over 4 plus 1/9 x cubed, 11/6 x squared, 34/15 x. 0 to 1, we get negative 1/4 plus 1/9 plus 11/6 plus 34/15. Okay, and then assuming my scratch work off to the side here is accurate, I got 713/180ths. Okay, and so there's a typical example of how to go through and calculate the flux across the surface. So the problems, you just need to go through and handle them in steps and compartmentalize them. Okay, so you want to think of it in terms of steps. So step 1, you want to go through and find ds. Step 2, we go through and kind of construct the f dot ds. So you use your ds, but you also have to figure out what f is. So here's step 2. All this Okay, step 2. And then once you've got that done, then that's the hardest part. From there, it's just dot product and then just evaluating. So let's try another one. See if we can get this one as well. All right, so we got f of x, y, z equals xi plus yj plus zk. S is the sphere with radius 1 at the origin. Okay, so with this one, a sphere is a closed object, right? So we have, bottom and top, we have sides, front and back. And so that means that when you're going through and doing the DS part, where you have to take into account the orientation of the surface, whether you want upward pointing normal vectors, or downward pointing normal vectors, which we just finished discussing a few minutes ago. You need to have both. We need to have both. We need to have upward for the top half and downward for the bottom half. So there's a couple ways you could go through and do this. You could go through and represent this in terms of x, y, and z, and then solve for z and have a top half and a bottom half. If you do that, when you do that, you need to do 2 integrals. One for when you're going to have the top half, right? So that one is going to have a upward pointing ds, upward pointing normal vectors, and then the other one you want to have downward. Or what you can do is you can use, you can go through and parameterize the surface, and if you parameterize it, then you don't need, you can do it with just 1 integral. Now, which is easier? It depends. The parametric part does have more work. There's more steps to it. So that's worth considering. However, you only have to do 1 integral, so it saves you some time and effort in that regard. So intentionally, I'm going to go through and use parametric to do the problem, just as a counterpoint to the way that we did the last one. All right. If you've got a sphere of radius 1, we know the equation is x squared plus y squared plus z squared equals 1. If we want to go through and parameterize this surface, it's a sphere. Parameterizing a surface that is a sphere, we go through and we use spherical coordinates. So you get x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. We also know that x squared plus y squared plus z squared equals rho squared. And then looking at our equation up here, this tells us x squared plus y squared plus z squared equals 1. So we can pop that in. We get 1 equals rho squared, which tells us that rho equals 1. Taking that, plugging it in, we get x equals sine phi cosine theta, y equals sine phi sine theta, and z equals cosine phi. Then parameterize, plugging this into our vector form, we'll have r, and we're going to switch over to u's and v's, and then we're going to have sine u cosine vi plus sine u sine v j plus cosine uk. Okay, with all that done, so a bunch of work there that you don't have to, you can skip over if you just solve for z. in the original equation. So this is part of all the busy work in the parametric form. So it does take more, there are more steps to it because of that. From there, the next thing we want to do is we want to go through and form ds. ds is RU cross RV. Okay, very simple. So this is, in some ways, the parametric version is easier. You don't have, 6 different choices to make. You don't have to figure out upward or downward. That'll be taken care of. And so here we're going to do R of U. That's going to be cosine U cosine VI plus cosine U sine VJ minus sine UK. And then RV, we're going to get sine U minus sine U sine VI plus sine U cosine VJ. And then there's no V's over here, so the derivative is 0. And so the K term is eliminated. All right, next we want to go through and calculate the cross product, right? So we need RU cross RV. So we'll move to the next page for that. RU cross RV. We're going to have I, J, K, and then we've got cosine U cosine V, cosine U sine V, and negative sine U, and sine U sine V, and negative sine U sine V, and sine U cosine V. All right, let's just check those. Those are from my notes. Is that correct? So we've got cosine U cosine V, cosine U sine V, cosine U cosine V, cosine U sine V. That's correct. And then negative sine U, negative sine U, negative sine U sine V. Yep. And then finally sine U cosine V. Yep. All right. For our cross product, we're going to have I, then we do this times this. So we're going to have, 0 minus a negative sine squared cosine V. So the double negative, we're going to get sine squared U cosine V minus J. This times this. So we're going to have triple negative there. So minus sine squared U sine V, and then plus K. And we get sine U cosine squared V. And then minus a negative, so double negative plus sine U cosine U sine squared V. All right, and then if you factored out the sine U cosine U here, you'd end up with cosine squared plus sine squared, which is 1. So this whole thing is going to simplify into sine U cosine U. Okay, so once we've got RU cross RV, just like in the last one, the next thing we want to do is to go through and form our F dot ds. All right, so what is F? F is given by this, but we want to change everything over into U's and V's. How do we do that? Well, you can use this definition here. This is X, this is Y, this is Z. Normally I would say to just use this, but we left it in terms of phi's and thetas. So just use this for X, this for Y, and this for Z. Whenever you've got a vector function, you can change over into the parametric equation by setting X equal to the X component, Y equal to the Y component, and Z equal to the Z component. All right, so looking over here, what are we going to have? We're taking this and putting it where the X is. We're taking this and putting it where the Y is. And we're taking this and putting it where the Z, and they're just right in order. Very simple. So we're going to have sine U cosine VI All right. And then next is yj. So y is sine u sine v. We'll have sine u sine vj. And then next we have zk, and zk is z is cosine u, so we're going to have cosine uk. All right, and then that's f, except translated over into u's and v's, and we want to dot that with ds, which is written right here. So we've got sine squared u cosine v I, and then double negative there, so plus sine squared u sine v j, and then plus sine u cosine u k. And all of that dA, and over the domain for u and v. All right, let's go through and do the dot product here, and then we'll figure out what our bound should be. All right, so the dot product, we're going to multiply the I components together, j components, k components. Sine u cos v, sine squared u cos v. So we're going to get sine cubed u cosine squared v. Sine u sine v times sine squared sine. So we're going to get sine cubed u sine squared v. And then cosine u times sine u cosine u. We're going to get sine u cosine squared u. All right, dA over d. And then if we factored out these sine cubes, then we would have sine squared plus cosine squared, which is 1. And so we can simplify that into sine cubed u plus sine u cosine squared v. Oop, not v, sorry. There we go. And then as far as order of integration here, what are the bounds? Well, we never figured them out, but if we're going through and defining our sphere, what do we want the bounds to be for phi's and thetas? Well, since it's the whole sphere, phi goes from 0 to pi. And then theta goes from 0 to 2 pi. Since the bounds here are constants, the order of integration doesn't matter. So we could do, let's do u first, and then v will be really easy, right? So what did we say u was? So u is our phi values, which goes from 0 to pi. So let's do 0 to pi. And then we'll do 0 to 2 pi, right? There are no v's in here, so that one will be really easy. So we've got du dv. All right. If we're integrating, with respect to u here, integrating sine cubed, we need to go through and use our trig techniques from back in Calc 2. And then this one's already set up for that, where we've got a u and then a du. So we need to pull out one of the signs and then take the rest of the signs and turn them into cosines. So we've got 0 to 2 pi, 0 to pi, pull out two of the signs, two of the signs. Turn those others into cosines using the identity 1 minus cosine squared. And then we could go through and combine it. Oh, does this actually work? Oh, I need to check this. My notes disagree with this. Let's see, is this correct? according to this, if we were to go through and combine these, the cosine squareds are going to cancel, and this is going to turn just into sine of u du dv. So let me take a look at that and check it. All right, I checked it. It is correct. I figured out what the problem is with my notes. Technically, this problem was supposed to have a z squared. But you know what? The problem is a lot easier without the z squared. So let's just do it without the z squared. If you had a z, if you did do it with a z squared, then we would have cosine cubed here, which would make it would add a little bit more work here at the end in terms of going through, and you'd actually have to do the u substitution. But without that, this simplifies really nicely. And so let's just do this, because again, the point is just to get to the answer here at this point. So the antiderivative of sine is going to be negative cosine of u evaluated 0 to pi plug in pi, and when you plug in pi, you get -1. So we're going to get -1, so that's going to be 1 minus, and then plug in 0, and you're going to get minus another -1. Anyway, lots of negatives in there. The whole thing's going to simplify into 2, 0 to 2 pi dv. We get 2 times 2 pi. That's going to be 4 pi. All right, and that is our answer. Okay, so interpreting this, I can't remember if we discussed the interpretation for the first one, but the idea is that we're trying to find the flow through the object, and that's what that answer is. So that's going to be the amount of flow. So assuming the vector field looked like this and we had a sphere, then the amount of flow through the sphere is going to end up being 4 pi. The answer does kind of make some sense, that you get, well, at least you get a positive answer, right? If you think about what x plus y plus z looks like in terms of, if you were to graph it, right? It's going to be values that are pointing away from the origin. So just for example, just for simplicity's sake, let's just say z were 0 and we had x and y were 1, then the vector here is going to look like that. If you did the equivalent here, you're going to get a vector that looks like that. The equivalent here is going to be a vector that looks like that. If you took all x, y, and z are all 1, then it's going to be a vector here, and it's going to be outward. It's a little bit harder to interpret that one. But if you think about just then superimposing on top of that, so essentially you've got these vectors that are all pointing outward. You think about superimposing on top of that a sphere, or part of a sphere. Let's just do part of one. Then the vectors are pointing, the vector field vectors are pointing through the sphere. And so that's what you how do I say this? If you're going to get a positive value for the flux, that's what you'd expect. So you'd expect that would go along with ending up getting a positive value for the flux, which is what we got, which is 4 pi. Would the problem have been significantly changed if z were squared the way that it was supposed to be in my notes? It would be a little less obvious, right? Because then if you do that, then your z values that are above the axis are going to point above the xy plane are going to point up, and your z values below are going to also point up. And so we're going to have upward pointing z's in both cases, which would make it at least a little bit more in doubt as far as what the flux would end up being, whether it's going to be positive or negative. But a positive flux goes along with having flow through the surface, outward through the surface, and that does align with what we would expect from graphing here we've got our vector field, here we've got our normal vectors, and we could see they do point in the same direction. All right, so our answer does end up making some sense. Okay, I did one more example here. I have no idea how long this video is going to end up being. Hopefully it's not too long. So we've got f of x, y, z. That is given by yi plus z minus y j plus xk. And then S is the surface of the tetrahedron. Zero, 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 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so this one's a little different than the others, which does make it more difficult. What you should do first is try and get your hand on what type of an object we're talking about here. What is the surface? If you were to go through and plot this, what you'll get is you'll get, what points do you have? You have 0, 0, 0. You'll have 1, 0, 0. Oh, sorry, that's 0, 0, 1. You'll have 1, 0, 0, and you'll have 0, 1, 0. You get those 4 points. If you connect those, we get this pyramid type shape, tetrahedron. Okay, so the thing that makes this problem significantly, at least longer than the previous problems, first of all, this is a closed surface. But not only that, it's a closed surface that has 4 distinct sides to it. So we have the bottom here. We have the left side. We have the back. And then I'm not going to draw on it, but we also have the front, the side that's facing us. And so if you're going to go through and calculate the flux through a closed surface, and that means it needs to be outward through all, outward through the sides, and you've got 4 sides, that means you've got 4 calculations to do. 1, 2, 3, and then the one that's facing us. Let's call that vector that one. Let's call that vector the one that's for the front. So you've got 4 different pieces to do. All right, so let's do the hardest one first. Let's do the one that's facing us. So the one that's facing us, we need to go through and find the equation for this plane that is in the first octant. Okay, the part that's not part of the coordinate planes. All right, how do we do that? If we want to go through and find the equation for this plane, well, it's an equation of a plane and it's got 3 points on it. We did find equations of planes that had 3 points on them back in the very beginning of this course. If you go back and watch our lines and planes video, we went through that process. The way that you do that is you go through and you define a vector between 2 points, a vector between the other 2, and then once you've got 2 vectors that are on the plane, you can go through and find their cross product to find the normal vector. So let's go ahead and do that. Let's define this vector here. All right, so that vector there, it starts at 1, 0, 0, and it terminates at 0, 0, 1. So you would take this coordinate and subtract this coordinate. We'll call that vector u. So vector u is going to have 0, minus 1, 0, minus 0, and 1, minus 0. Okay. And then let's go through and do this guy for the second vector. So vector v. So we're going to take, this is the termination point. This is the initial point. So just subtract. We have 0, minus 1. So we're going to have negative 1, 1 minus 0, 1, and 0 minus 0, 0. We've got u and v. Do u cross v. We've got I, j, k. negative 1, 0, 1, negative 1, 1, 0. That's I times 0 minus 1 minus j times 1 plus k times negative 1. And so we get negative I minus j minus k. Take those, plug them into the plane equation, and you're going to get negative 1 times, and then we just need to use one of these, not that point, use one of these 3 points, because this point is not on that plane. Use one of these 3. We'll just use the first one, which is 1. So we'll have x minus 1 minus 1 times y minus 0 minus 1 times z minus 0 equals 0, which is going to turn into what we got. This is negative x plus 1 minus y minus z equals 0, or if you prefer, x plus y plus z equals 1. And if you're one of those people who looked at it and just immediately thought of that without actually doing all these calculations, then great, save yourself a few minutes. All right, so now that we have an equation for this front surface, we can go through and find the flux across it, okay? So when we find the flux, start off F dot ds, all right? And ds, when we're going through and finding for the ds for this plane here, we want upward pointing, because upward is going to be outward. Outward is, for this plane here, the front that's facing us, if you tack down a normal vector onto it, all the normal vectors onto it are going to be pointing up. And so since we want an upward pointing normal vector, that means negative partial of z with respect to xi minus partial of z with respect to yj plus k. So we need the partial of z with respect to x. Oh, well, I guess first you want to go through and take this and rewrite it so that z is by itself, so that we have our surface defined in terms of z. 1 minus x minus y, right? If we have x plus y plus z equals 1, we can rewrite that as z equals 1 minus x minus y. And then z differentiated with respect to x is going to be negative 1. Z differentiated with respect to y is also going to be negative 1. And then we can pop all those together to get our ds. It's going to be negative negative 1. So we're just going to get I, negative negative 1. So we're just going to get j and then k. All right. And so that's our ds. And then we need to figure out f. All right, what's f? F is this. Okay. And the way that you translate f over, when you substitute f into your double integral, you need to have only 2 variables. To get down to 2 variables, what you want to do is replace whichever variable your surface is defined in terms of, you want to replace that variable. And our surface is defined in terms of z. So we want to replace z's with 1 minus x minus y. All right, so what do we have? So y is fine. Don't replace that one. That one's fine. So we're going to have yi. And then, wait, what's next? Then we're going to have z minus y. Oh, we do want to replace z's. So replace z with 1 minus x minus y. That's z, right? And then minus y. Minus an additional y. J. And then what's left? We have plus xk. All right, and so that's our f, except in terms of x and y. Then we want to dot it with our ds. I, j, k, dA. Okay, over domain D, over the x and y values. All right, so now we can go through and calculate our dot product. We've got yi times, multiply component y. So we've got y times 1, that's going to be y. And then we've got 1 minus x minus 2y times 1. That's going to be 1 minus x minus 2y. And then x times 1 is just x. dA, d, all right. And then let's simplify this a little bit. We've got, oh, the x's cancel. That's nice. We've got y with a negative 2y. That's going to give us down to negative y. So we have 1 minus y dA over d. And then the question is, what am I integrating over? What is my d? D is the domain. It's all the x and y values. So what x and y region are we integrating over? Well, if you take this as our surface, then the base for that surface, that's going to be the shadow. That's, that's what you'd see if you look straight down. You're only going to see this red stuff, right? The red, that's the only part of the surface you're going to see. You're going to see the red part. And so you could go through and just sketch that for yourself if you want, or not. It's up to you. Get 1, 1. I'm going to sketch it because I think it helps people. So that's the object that we're seeing, except in two dimensions, right? And we've got, this is x versus y. What's the equation for this? There's a bunch of different ways you can get it. One way is just by looking at it. This is y equals 1 minus x. The other way is to take your equation here, plug in z equals 0. If you make z equal to 0, then you have x plus y equals 1, or y equals 1 minus x. But anyway, so this is the region we're integrating across. That's the base. It's type 1 or type 2. If you have a choice, I recommend doing vertical rectangles here that we're going to add across. And so we're doing top to bottom and then left to right. So if we're doing top to bottom and then left to right, top to bottom would be from 0 to 1 minus x, and then 0 to 1, and we get 1 minus y dy dx. 0 to 1, antiderivative of 1 is y, minus 1 minus y is second over 2, 0 to 1 minus x dx. What's this going to be? We're going to need some space here to simplify. 0 to 1, this is 1 minus x. I guess let's just write this 1 minus x squared over 2 dx. All right, 1 minus x. All right, so if you squared this out, we're going to have 1 over 2. So we're going to have negative 1/2 for the first piece. Squared this out, you're going to have negative 2x for the next one over 2. It's going to be plus 1 plus x. And then finally, we're going to have x squared. So we're going to have minus 1/2 x squared dx. What do we got here? This cancels with this. 0 to 1. 1 minus 1/2. That's going to be 1/2 minus 1/2 x squared dx. And then we'll work our way upward here. This is, I want to integrate next. Antiderivative of 1/2. It's going to be 1/2 x minus, then we get x to the third over 3. That's going to be 1/6 x to the third. 0 to 1. Plug that in. We get 1/2 minus 1/6. Right, so that's 3/6 minus 1/6. That's 2/6, or 1/3. All right, so we got 1/3. So what is that? What is that 1/3? That's going to be the flow from our vector field through this front pane that's kind of sticking out toward us. Now that's not the flux across the entire closed surface. That's just one part of the flux. We still have the other 3 sides to go through and calculate the flux across, if we're going to calculate the flux that's going out from the inside of that surface. And so we've got 2 more to go. I intentionally want to do this one because we get to actually see the variation in the DS's. So you're going to get to see all the different DS's, which can be useful, can be helpful to see that. All right, so next thing we want to do, we want to go through and handle f dot ds. Let's pick another side to do. Let's do the bottom next. I think the bottom makes the most sense to do after that. So the bottom, what is the equation for the bottom? Right, so this pane that we just did had equation x plus y plus z equals 1, or z equals 1 minus x minus y. What do we know about this bottom piece? Well, the equation for that is z equals 0. So we have z equals 0. That's our That's our surface, the part of our surface anyway. All right, and what about ds? What do we want for ds? We know ds, when we have z defined, equals negative partial of z with respect to xi minus partial of z with respect to yj plus k. All right, that's the ds for upward. Do we want upward? No, the normal vector, assuming we're trying to find flow out of this surface, the flow out of this surface is going to be downward through the bottom. So this is the case where we want to use the negative of this. I talked about this, many moons ago in this video. This video is going to be like 7 hours long or something. Then so instead of doing minus minus plus, you want to go plus plus minus. So you just want to negate it. And so we have the opposite. All right, so once we've got our surface and we've got our ds, we can combine them to figure out, what the ds is going to be for actually evaluating. All right, so to do that, we need to take z and differentiate with respect to x. Oh, look at that, it's 0. Take z, differentiate with respect to y. Oh, look at that, it's also 0. Pop those in, and what are you going to get? ds is going to equal negative k. Super simple. All right, and so now we can start changing stuff over. All right, so our ds is going to be negative k. We need to figure out what our f is going to be. What is our f going to be? Well, so we've talked about this. When you go through and figure out what your f is, you want to get it down to 2 variables. And the way that you do that, leave, in this case, since we have the equation for z, leave x and y alone, but substitute in for z. You want to leave x and y alone, but substitute in for z. I guess I should look before I moved it. All right, so we've got yi, that one stays as it is. So we're going to have yi. And then if z, and then we have z minus y, so z is 0, right? So we're going to have 0 minus, so we're just going to have 1 minus yj instead of z minus y. And then xk, so that one just stays as it is. And so you can see, again, I'm still just going through and finding f by plugging my surface in, and other than that, not making any other changes. And now we dot that with negative k dA over domain, over the domain, which is all the xy values. All right, and so what happens after we do the dot product? We just get xk times negative k, we just get negative x dA over d. And then the question is, oh, what d values, what's the domain? What am I going through and integrating across for x and y? Well, if we go back to our picture, it's this region. That's the region we're integrating across. And so it's the same as what we just did. We just want to use 1 minus x again. All right, so this is going to equal the integral 0 to 1 minus x, 0 to 1, negative x, dy dx. So we get 0 to 1. The antiderivative of this with respect to y is negative xy, 0 to 1 minus x, dx, 0 to 1, plug in 1 minus x, we get negative x times 1 minus x, dx, plug in 0, you get 0, right? And then let's just go ahead and move upward here. So we've got 0 to 1. We can multiply this out. This is negative x plus x squared dx. So we're going to get negative x squared over 2 minus x to the third over 3. 0 to 1. Plug that in. You get negative 1/2 plus 1/3. That's negative 3/6 plus 2/6. We're going to have negative 1/6. Is that right? Yeah, negative 3/6 plus 2/6. Yeah, that's right. And so that's our flow out through the bottom is negative 1/6. What does it mean if you get a negative flow? It means that it's working in the opposite direction. So that actually means that for the bottom, the flow is actually upward into the object, because if we'd gotten a positive value, then we would have had downward flow. A negative value means that we have upward flow through the bottom. Okay, so that's 2 down. We still have 2 more to go. We need to do the side here that's on the xz plane and the back, which is on the yz plane. All right, so we're still doing f dot ds over s. All right, and this time, let's go ahead and take one more look at just going back and forth. Sorry. Let's do the left side here next. What's the equation for that? For the left-hand side. So that's the xz plane. The equation is y equals 0. All right, if we're doing y equals 0, that means we need a ds that is in terms of y. The ds for y is you take y and you differentiate with respect to x, I, plus j, and then minus y differentiated with respect to zk. This ds points to the right. How can we tell? Because of the plus j. J, the default for j is to point is, j is our unit vector that points one unit to the right. And so this is a rightward pointing ds. Do we want a rightward pointing ds? If we go back and look at our picture, if we're calculating the outward flow, this is on the left-hand side, so we're calculating the flow that's to the left. So we want a leftward pointing ds, or leftward pointing normal vector. So you want to go through negate all of this. It should be minus and plus like that. All right, so now this will point to the left. Once we've done that, the only thing left to do is to take our equation for our surface and calculate the partial with respect to x. Oh, it's 0. Y differential with respect to 0. Z, it's 0. And then pop those in and you get ds equals just negative j. All right, and so now we can go through and take that, plug it in here, and translate over the f at the same time. So again, when you're going through and figuring out what your f is here, you want to leave two of the variables alone and substitute for the other one. You're going to substitute for the one that your surface is in terms of. So what we want to do is wherever the y's are, we want to put 0, and then we want to leave the x's and z's alone. All right, so y's are going to be 0. Up there goes that one. Leave the z's alone though. So we're going to have zj plus xk. That's what we get if we go ahead and substitute y equals 0 into our vector field, into our f definition. And we want to dot that with ds, which we just found. That is minus j. If you go ahead and calculate that, zj plus xk dotted with negative j, you're going to get negative z, dA over d. All right, and then so the question becomes, what are my bounds? What are my x and z values that I'm going to be integrating across here for this thing that's on the left-hand side? Well, if you if you look at it, what is it? We've got the x values that are going from 1, 0, 0 to the z values that are going to 0, 0, 1. So we've got x from 1. Oh, I'm trying to describe this. It's so much easier just to draw a picture, right? It looks like this. Z, x, 1, 1. Oh, look at that. It looks exactly the same, except we have z and x instead of y and x. So that means this equation is z equals 1 minus x. And so we can just go through and do that. So we're going to have the integral negative z dz dx 0 to 1 minus x, 0 to 1. And if you're just a little bit clever here, you can look back. What would we integrate? Oh, actually, no, we can't use this result. I thought we could use this result, but the variables are different. Oops. So I guess we can go ahead and just do this one. So we got 0 to 1. This is negative z squared over 2, 0 to 1 minus x, dx, 0 to 1. We get negative 1 minus x squared over 2 dx. And if we square this out, we're going to get 1. So it's going to be negative 1/2. We're going to get negative 2x over 2 negate. So we're going to get plus x. And then we're going to get x squared minus x squared over 2 dx equals, and then we can go through and integrate. This is going to be negative x over 2 plus x squared over 2 minus x cubed over 6, 0 to 1. And you're going to get negative 1/2 plus 1/2 minus 1/6 equals negative 1. I knew that was going to happen. Grr. All right, it is negative 1/6 again. Oh well. I think the way that you needed to do this, if you wanted to just kind of cheat and use this previous result, is you needed to go through and make this 1 minus z, right? Is that right? Then it would have been lined up. Yeah, 1 minus z. Yeah, so instead, what you needed to do is, instead of doing top to bottom here like this, if you'd gone through and done it like this instead, then this would not have been, I mean, it is still z equals 1 minus x, but it also would have been x equals 1 minus z. And then you could have done, yeah, and this could have been 1 minus z and then 0 to 1, and then it would have matched. And in any case, it didn't take that long to do this. So we've got negative 1/6 again. And then what's going to happen with the last side? All right, so the last side is the back. What is the equation for the back? Right, it's going to be x equals 0, right? So we've got one more, f dot ds, x equals 0. The ds for x is I minus x differentiated with respect to yj minus x differentiated with respect to zk. Now, what is true about this ds format, the default one? The default one points forward, right? Points in the positive x direction. Is that what we want? Go back again. Nope. For this object, we want the x that's going to point in the negative x direction, that's going to point backward. So we want to go through and negate this. And that's our right, that's the correct one. And then to go through and actually calculate this, we need to go through and calculate some partials. So x differentiated with respect to y, the derivative of 0 with respect to y is 0. The derivative of 0 with respect to z is also 0. And then if you pop those in, you get ds equals negative I. All right, and then finally we can go through and change f over. When you do, where the x's are, put zeros, and then leave the y's and j's alone. What are we going to get? So we're leaving the y's and j's alone. That means that we're still going to have yi, we're still going to have z minus yj, the x is 0, so that gets rid of the k term. So we're going to have, what is that, yi and z minus yj. Yi and z minus yj. All right, so that's our definition for f, except with our surface plugged in to get it down to just 2 variables. And then we're going to go through and dot it with ds, which is negative I. And what happens? We're going to get negative y dA over d. And this time, can we be clever this time? So this, you're looking really right at it, so it's going to be the same graph. But if we went through and were to just sketch this without the 2 dimensions, without the 3 dimensions, we would get the following picture. So we've got 1, 1, and then this side here. So now this is in terms of just y's and z's. So this is z equals 1 minus y, right? If this were the z-axis, and this is the y-axis, and we could do top to bottom, right? And if we do that, what are we going to get? We're going to get the integral from 0 to 1 minus y, 0 to 1, dz to dy. Is that right? So from 0 to 1 minus y, and then from 0, oh, hold on, no. Right, no, wait, that's right, I'm sorry. I'm getting confused with myself here. In any case, you can kind of guess what's going to happen here. I'm just kind of screwing around. what did we have here? We've got negative y, integral to 1 minus y. If you look at the previous one, integral 0 to 1 minus x, negative x. It's the same thing again. So we're just going to get negative 1/6 one more time. All right. And so that gives us the flow through that side. Once we have all of the flows together, we can go through and just combine them. All right. So to get the cumulative flow through the surface, we just combine them. All right. So what was the first one we got? So the first one was 1/3. So that's the flow through the front. All right. And that was positive. So we got 1/3. That was the flow through the front. And then through the bottom, we got negative 1/6. So that's a negative flow. So it was actually flowing upward through the bottom, not downward. And then through the left side, we got negative. So instead of flowing outward through the left, instead it's flowing inward. And then we got negative 1/6 again through the back. And if we combine all of those, we end up getting 1/3 minus, oh, actually, hold on. What am I doing here? It's about to get common, but these cancel. And so you get negative 1/6. And that is the cumulative flow for the object. And so the cumulative flow is actually, what that means, since it's negative and outward is positive, is it means that we have cumulative inward flow. So there's cumulative flow inside the object, toward the center of the object. Well, not toward the center, but inside the object, through the surface, through the sides. We're flowing into this tetrahedron instead of outside of it. Okay, that is the video. I need to go through and chop it up now, and we'll see how long it is. Hopefully it's not more than 2.5 hours long. All right, thank you for watching, and hopefully you got something out of that. See you next time.